So the question comes up of when do we use the sample distribution versus population? So I'm going to do this. And I'm going to throw an example up here to illustrate this. So let's say we have a population with mean of 830 and standard deviation of 80. Find the probability that one, a randomly selected item has a value greater than 850. So this is the probability that a randomly selected item has a value greater than 850. So P of X is greater than 850. We selected one item and we're looking at the value of that one item. So this is just a regular normal probability. Normal CDF from 850 positive infinity with a mean of 830 and a standard deviation of 80. So if we punch this in the calculator, second distribution, normal CDF, 850, positive infinity, mean of 830, and a standard deviation of 80. And we get that probability of 0.4013. So the second question then we're going to ask is find the probability that a randomly selected sample of 25 items has a mean greater than 850. So this is now a sample. It is more than one item. It's 25 items, and we're looking at the mean of the item. We're not looking. So up here, take this to move on for me here. Up here, we were looking at one item. We selected one item and we wanted to know the value of that item. Down here, we've selected a sample and we're not looking at a single value. We're looking at the mean of a sample. So that tells us that this is a sampling distribution. So we're not looking at just the probability that a single value is greater than 850. We're looking at the probability that X bar, or a sample mean, is greater than 850. So it's still normal CDF, and we're still going from 850 to positive infinity. Now in the sampling distribution, the mean is the same as the population mean. So it's still going to be 830 for the mean. What changes is the standard deviation. The standard deviation will be the population standard deviation divided by the square root of the sample size, by the square root of 25 in this case. So on the calculator, it's second distribution, normal CDF, still going from 850 to positive infinity, still a mean of 830, but now this is going to be 80 divided by the square root of 25. And we get 0.1056. So there's the difference. The fact that this one was a sample. We're looking at the mean of a sample rather than just the value of a single item. Does that clear it up for you a little bit?
Yeah, so if it says like a population or I think I had wrote it down. Yeah, it does.
Okay, so yeah, so the key is what you are selecting. If you're selecting one item from the population, then it's just a normal probability. If you're selecting a group from the population and looking at the mean of that group, then you're looking at a sampling distribution.
So I called it like a sample of a sample. Is that kind of what that is? Is sampling
Kind
of
of,
the
yeah.
sample?
It's the mean of the sampling distributions. Yes.
Okay.
Okay, can I ask you to continue that? So there's another time that we use a different formula for that standard deviation. When does that come into play?
So that is if we're dealing with a proportion. So let's say that we have, well, let's say we predict now let's make it a little easier. What is the probability of a sample of 100 voters giving at least 60% approval rating or approval for, we'll say option A, when there really is no preference? So the first part here is a little subtle. When there really is no preference, that means that the population proportion is 0.50, 50%, no preference, 50-50. So we're asking, what is the probability of this sample of 100 voters? So again, we're taking a sample. We're not just looking at one voter. We're looking at a group that we've selected. So we're looking at the probability that the mean of the proportions of the sample proportions, and I should write it like this, that the mu of the sample proportions is greater than or equal to 0.6. So this will be a normal CDF from 0.6. Now, since it's a proportion, it can never go higher than 1. So 0.6 up to 1. The population mean, if there's no preference, we're assuming that's 0.5. And now the standard deviation or the standard error for a population proportion is the square root. It's the square root of p times 1 minus p over n. So this will be 0.5 times 1 minus 0.5 divided by 100. So if I enter that in the calculator, second distribution, normal CDF, 0.6 to 1. 0.5 is our population mean, and then this is going to be the square root of 0.5 times 1 minus 0.5 divided by 100, and that's all within the square root. This will be 0.0228. So just over a 2% chance of getting more than 60% at a sample of 100, if the true proportion really is just 50%. So that's where you use that other formulas when we're looking at trying to estimate a population proportion.
Thank you.
You're welcome. So this leads us into what we're looking at for tonight. Let's go back to that first example. We have the mean of 830 and a standard deviation of 80. If I'm taking a sample of 25 items, so if n equals 25, between what two values will the middle, oops, will the middle 90% of the data fall? So this is combining a couple of things from the last couple of weeks. We're looking at sampling distribution, but we're also looking at some of that normal probability stuff, where we have the bell curve and we want the middle 90%. So at 90% out of the middle here. If there's 90% in the middle, that means there's 10% outside of it. And since we're taking the 90% out of the middle, the 10% is split 5% to each side. So that means this cutoff here has an area to the left of it of 0.05. This cutoff has an area to the left of it of 5 plus 90 is 95, so 0.95. So we need to do both of those inverse normals. So on the calculator, of course, this is the inverse normal command, option 3. And so it's going to be inverse normal. We'll do the 0.05 first with the mean of 830 and the standard deviation of 80. Now it's still a sample of 25. So 80 divided by the square root of 25. Now I do have my TI-84, my CE calculator here on screen tonight. I'm going to do this the way most of your calculators that are just a TI-84 plus C version or above, silver version or above. Your calculators only give the left tail probability. So I'm going to enter it as left tail, and I'll change that setting when I get down to it. So 0.05 is the left tail, mean of 830. Standard deviation is 80 divided by the square root of my sample size, which is 25. And I am changing this to a left tail because that is the standard setting on your calculators that are not CE, that do not have that option. So I get 803.68 is the one end. The other end, second distribution, inverse normal. I'm going to change this to 0.95 and everything else is going to change the same, stay the same. I get 856.32 on the other end. So this is between 803.68, sorry, not 58, and 856.32. So I would expect 90% of the samples that I take, of the samples of 25 items, I would expect those means to be between 803.68 and 856.32. Now, for those of you that may have the CE calculator, I'm going to show you one of the advantages of it. So I'm going to put in 0.9 for 90%. The mean and the standard deviation are going to stay the same. And this time I'm going to select center because we want the 90% out of the center. And it gives me those two values that I just had. It gives me that interval, 803.68 to 856.32. So there are some advantages to the newer version of the calculator. It's also about $15 more. So if that's worth the $15 extra, that's up to you to judge. Anyway, for those of you that do have the CE calculator, you do have that option.
So can I ask you a question back to the curve here? You said that the 10% was split.
Yep.
But why is it only 5% on this side, but 95 in the middle? Why wouldn't
Well,
it be?
so it's 5% on each side. But remember, the inverse normal on most of your calculators only looks at the left tail or the left side.
Okay.
So to the left of this is 0.05. To the left of this one is the 0.05 plus the 90.
Okay. And so when you do the CE, because I had to buy a calculator, I didn't know which one. So if I just do the CE and I'm looking for the middle, I would just do 90 and put the center.
Yep, you could actually just like we saw here. You could just put in. Oops, that's not what I want. Let's. Yeah, you can just put in 90.9. Select center. Get your mean and standard deviation in there. Oops, I got select center. And it'll give you both numbers all at once. So yes, exactly like that.
Okay. Okay.
Okay, so on to our new stuff for this week then. What is this leading us into? What it's leading us into is estimating population parameters. And we're going to start talking about estimating population means. And our first method of estimating a mean, and the simplest method, is called a point estimate. And all a point estimate is we select a sample, of whatever our desired size is. So we'll call it n. And then we find the mean of that sample. And then our estimate is simply to say that the population mean should be close to that sample mean. So again, if we're looking at that bell curve, we know that the sample means are going to be distributed around the population mean. But it's still possible for the sample means to have a value that's quite a bit smaller or quite a bit larger than the actual population mean. So the point estimate could be a good estimate, but it might not be a very good estimate of that population parameter. So we'd like to come up with something a little bit better. Of course, we could make it better by making a larger sample size. The bigger the sample size is, the narrower this curve gets. So the closer to the population mean that those sample means are likely to be. Taking a bigger sample size takes more resources, takes more time. Time equals money. It just takes more to do that. So what we do is we use something called an interval estimate. And an interval estimate is what we're going to say is, well, you know what? We want to know how far we go out from that sample mean or from that population mean to collect a certain percentage of the sample means. And then we're going to use that distance, that size, we refer to it as a margin of error, to create an interval around our point estimate. Now, there's a lot of ways of doing the interval estimate. The interval estimate we use is called a confidence interval. It's actually called a Wall confidence interval, but we don't use, our textbook doesn't use that term. Wall, W-H-A-L, is the guy who invented it. And what it's saying is, if we look up here at this sampling distribution, we don't know what the population mean is, but we do know that a certain percentage has to be within so many standard deviations of that mean. And so here we said 90% was what we were looking for in this example. Let's do that again. If we wanted to have 90% of all the sample means in that interval, we need to figure out how far do we have to go out. This distance is the margin of error. Then we take that margin of error and we would apply it to whatever our point estimate is. So let's look at how do we find, first of all, that margin of error. So the margin of error Some books refer to it as a bound on the error. Some textbooks abbreviate it with just an E, some with an ME. But that margin of error is equal to a critical z-value times that standard error of the means. Now the critical z-value, remember, a z-score is a number of standard deviations that we have to go on each side of the mean in this case. The standard error is just that standard deviation of the sample means. So it depends on whatever the population mean is. Let's look at an example here and go from there. So our example, let's see, where did I go? There we go. I'm just going to go straight forward here to say construct the 98% confidence interval. For the population mean if a sample of 53 items gives a mean of 28. The population mean or population standard deviation is known to be 7. So this last line here is very important. The population standard deviation is known to be 7. To find that standard error, remember that standard error is the population standard deviation over the square root of the sample size. We have to know the population standard deviation in order to calculate our standard error. 98%. 98% confidence interval means two things. One is, if we're looking up at the sampling distribution, we're going out far enough from the population mean that we're going to catch 98% of all those sample means. That is going to be used to find our critical z values. So z critical goes off of that 98%. The 98%, the confidence interval needs to come out of the middle of the curve. So if there's 98% inside, that means there's 2% outside. And just like our 10% was split both ways, the 2% is split each way. So that's 1% on each side. Now, if you have the CE calculator, you would just go 98%, 0.98 out of the center. We're going to work with the old version with the 1% on this side. And then this side, to the left is 1 plus 98, or 99%. So we're going to do those values here. Second distribution, 0.01. So let me get out of there. That's not the right function. Second distribution, there we go, inverse normal, 0.01 for a mean of 0, a standard deviation of 1. Why did I use a standard deviation of 1? Because I'm looking at a z-score here. This is just a standard normal. And I want the left tail. I get negative 2.326. If I do the right tail, the other side, second distribution, inverse normal, 0.99, mean of 0, standard deviation of 1. I get a positive 2.326. Now, another option is I could have left this as 0.01 on the right side, and I could have said I'm looking at the right tail. Now I'm going to get the 2.326. For a confidence interval, these two values will always be the same number, just one positive, one negative. So we'll use the positive as our Z critical. So 2.326. So then our margin of error is 2.326, that Z critical, times the standard error, which is going to be the standard deviation divided by the square root of the sample size, 53. So on the calculator, 2.326 times 7 divided by square root of 53. We get 2.271 is our margin of error. Our point estimate is just our sample standard or sample mean of 28. So then our interval is just that point estimate of 28 minus the margin of error to that point estimate of 28 plus the margin of error. So we're getting an interval of 25.729 to 30.271 is our 98% confidence interval. So we said the 98% meant we were going far enough out around that population or the center of that sampling distribution to get 98% of the sample means. What does that mean then for this interval? Well, it means we are 98% confident that the true population mean is somewhere in that range. Now, what we cannot say that there's a 98% chance that the true population mean is in that range, because it's not true. We have already created this range. Either the population mean is in it or it is not. Probability and chance do not apply to this anymore because we've already created it. Probability and chance only apply before we do something. We are 98% confident. What that is saying is if we repeated this process over and over again, 98% of the intervals created would contain the true population mean. Now that sounds really similar to saying there's a 98% chance that the true mean is in there, but it's a very important difference because we've already created the interval, chance doesn't apply anymore. So it's 98% confident that the mean is in there. Now, of course, the calculator has some built-in functions that make this process a lot easier. If we go to Stat, then we go over to the Tests menu. We go down to confidence intervals. This is a Z interval. Now we have two options for input. We either do the data input. This would mean I would have all of the, in this case, 53 items in my sample. I've had the value for each item in the sample and have to put it in the list and input it as a list, as data. I don't have that. I have the summary statistics of the sample. I have the size was 53 and the mean was 28. So here I have, this is sigma, that's the population standard deviation, which was given to be 7. The sample mean was 28. My sample size N was 53. Confidence level was 98%, so 0.98. I hit calculate. And there you go. We get the exact, pretty close to the exact same numbers we had here. 25.763 to 30.237. Round off errors is really the difference there. And you can see the calculator does it rather quickly.
So if we were doing it in Alex and we did that, is it going to count off? Because I know it's kind of,
Alex is programmed to accept the calculator answer.
okay.
So there was one important assumption here. I knew the population standard deviation. That's not always true. What if we do not know the population standard deviation? Now, I say it's not always true. What I really mean is it's very seldom true. If we don't know the population mean, chances are we don't know the standard deviation either. So this is a more likely scenario. So what we're going to do is we're going to do two things. One, we're going to use the sample standard deviation instead. But a smaller group, a sample standard deviation, the sample is going to be much smaller than the population. And a smaller group typically has a smaller standard deviation. So we would expect that sample standard deviation to be smaller than the population standard deviation. So we have to adjust for that. And the way we adjust for it is we use a t-distribution instead of a normal distribution. So the normal distribution is the z-distribution, the z-scores. The t-distribution is also bell curves, but the size of the bell curve is adjusted for the size of the sample. So a t-distribution requires that we know something called degrees of freedom. The degrees of freedom, or DF, is equal to the sample size minus 1. The smaller this is, the wider the bell curve gets. The more degrees of freedom, the narrower it gets. If we have an infinite number of degrees of freedom, the t-distribution becomes the normal distribution. So it's as we get smaller and smaller, the t-distribution adjusts for the fact that our sample standard deviation is going to be different from the population standard deviation. So let's look at an example for this. Where do we go? Now my notes are all messed up. Sorry for this. I missed a page out of here. That's why. Give me just a second. Oh, well, we'll just go on the fly here. So let's say that we have let's do this way. Find the 90% confidence interval for a population mean if a sample of 60 items gives a mean of 47 and a standard deviation of 11. So here we see that the standard deviation Standard deviation is from the sample. It's not a population standard deviation. It's a sample standard deviation. So that means we're going to use a T critical instead of a Z critical. We're still looking at a bell curve. It's a 90% interval. So that means we're taking 90% out of the middle. 10% is left out. And that 10% is split 5% to each side. So we're going to just find this cutoff, which is going to be 0.05 on this side. But we need to know the sample size is 60. So n equals 60. That means our degrees of freedom equals 59, one less than that. So we go to our calculator, second distribution, and you can see we have inverse T there for number 4. Our area to the left is 0.05. Our degrees of freedom is 59. We paste that in and we get a negative 1.671. So T critical is 1.671 is our value of T critical. Now I could proceed from there then to create my margin of error. My margin of error is going to be the 1.671 times my standard deviation of 11 divided by the square root of the sample size of 60 and get my margin of error. But I'm going to go ahead and use the calculator function now to do the rest of this. And I'm going to come back to that margin of error in a little bit. So I'm going to go to the calculator. I'm going to do stat and go over to tests. And option 8, there is T interval. That's what I want. I'm still entering my statistics. My sample mean was 47. My sample standard deviation was 11. My sample size was 60. And my confidence level is 90%, so 0.90. I hit enter and I get a interval 44.627 to 49.373. There's my interval. Now notice the calculator does not give me the margin of error, but I can find the margin of error rather quickly by just subtracting these two numbers. 49.373 minus 44.627 and dividing by 2 because the margin of error is half of that range. Minus 44.627. Now, since I forgot to put parentheses around that, I'm going to hit enter first and then divide by 2. I get a margin of error of 2.373. Had I gone through with this calculation, what would I have? 1.671 times 11 divided by the square root of 60, 2.373. Would have had the exact same margin of error. So the calculator shortens up that calculation considerably for me. Now, before I move on to estimating proportions, I want to talk about required sample size. So required sample size. I want to be, notice when I'm looking at my margin of error, the margin of error equals that Z critical or T critical times my population standard deviation divided by the square root of n. There's 3 factors that influence the size of this. One is the standard deviation. Well, the standard deviation comes from the data. We cannot change the standard deviation. So that one's kind of stuck. Z critical comes from the confidence level. I could change the size of the margin of error by changing the confidence level. Lower confidence level would equal smaller margin of error. But it's also a lower confidence level. We don't necessarily like that. I can also change the margin of error by changing the sample size. This is the easiest one to change because The confidence level is usually kind of determined by the situation of how vital it is that we get an accurate result. But the sample size is always pretty much up to us to decide how much data we want to collect. If the sample size gets larger, the margin also gives us a smaller margin of error. So we can turn around and say, okay, if we want to keep our margin of error small, how big of a sample do we need? If we take this formula here and solve it for n, we get n equals it's not margin, right? M equals our z critical times standard deviation over the desired margin of error, and that's all squared. So for example, let's say I want to find the minimum sample size required to produce a sample with a margin of error of no more than 4 if the population standard deviation is known to be 9. And we are using a 95% confidence level. So for this formula to work, we do have to know a standard deviation, or at least have an estimate of the population standard deviation. So we're going to be using a z score there, an inverse normal. Let's find that z critical. So to find z critical, we're using the bell curve. It's 95%. 95% is inside that curve, meaning there's 5% outside of that range, putting 2.5% on either end. So I'm going to do an inverse normal of the 2.5% or 0.025 to get that cutoff, knowing that these two numbers are the same, just one's negative and one's positive. So I do second distribution, inverse normal, 0.025, mean of 0, standard deviation of 1, because I am just looking for a z-score. And I do want the left tail. I get a negative 1.9599, so a 1.96 is z critical. 1.960. So my formula, n equals 1.960 is my z critical, right here, times my standard deviation, which is 9. Keep pulling stuff up accidentally there. Divided by my desired margin of error, which is 4. And that's all squared. So here, this is going to be, in parentheses, 1.960 times 9 divided by 4, close the parentheses, squared, 19.4481. Now, I need to round, we can't take a sample of 19.4. I need to round this. But remember, this is the minimum sample size, the minimum size of n. If we round down to 19, which is what that would normally round to, it's going to be too small. So we always round up for sample size. So n equals 20 is our required sample size here. Take a sample size of 20, we can reasonably expect the margin of error on our 95% interval will be 4 or less.
Sorry, question. So always
Yep.
round up even if it's not higher than 5?
Even though this is 19.4, we round up. If it were 19.1, we would round up to 20.
Okay, got it. Thank you.
You bet. So now let's look at confidence intervals for a population proportion. This is going to be the same concept. We have similar requirements as we did for our sampling distribution. And those requirements are that we reasonably expect n times p to be at least 10. So we reasonably expect at least 10 successes. And we expect n times 1 minus p to also be at least 10. So saying we reasonably expect at least 10 failures. Our sample size, little n, has to be less than 10% of the size of the population. And of course, it has to be a simple random sample from the population of interest. So we can't have any systematic biases in our sampling technique. For a sampling distribution or for a confidence interval for a population proportion, the margin of error is going to be a z critical. For a proportion, it's always going to use a z distribution, always the normal distribution, times the square root of p times 1 minus p over n. You'll recognize this as the standard error from our sampling distribution. Now, if we don't know the population proportion, we use the sample proportion. So we put p hat as the sample proportion that we could use there. So let's look at an example here and create our confidence interval. A random sample. (240 students). There's 187 passed statistics on their first try. Create a 90% confidence interval for the population proportion. So first, we need z critical. That comes from the 90%. So our bell curve, 90% is inside the interval, 10% is going to be outside. That 10% is once again split 5% to each side. So this is 0.05. I'm going to find this z critical value here. This will be negative. We want the positive version, but that's okay. We'll just take the positive of that. So second distribution, 0.05. Oops, this one. Second distribution, 0.05. Mean of 0, standard deviation of 1, and left tail. We get a negative 1.645, so this is just going to be 1.645. Is our z critical. Now I can continue to create my margin of error. I'll go at least that far. It requires that I know my point estimate of p, my p hat, which is going to be 187 divided by 240, giving us 0.7792. Now that's rounded. So my margin of error is going to be the 1.645 times the square root of 0.7792 times 1 minus 0.7792 over my sample size of 240. So let's calculate it. 1.645 times the square root of 0.7792 times 1 minus 0.7792 divided by 240. We get, oh, what did I go wrong there? There we go. 0.0440. So that means my confidence interval is my point estimate of 0.7792 minus my margin of error, 0.0440, to that point estimate of 0.7792 plus the margin of error of 0.0440. So subtracting this gives us 0.7352 to what is that? 0.8232, I believe. And again, the calculator has a built-in function for this. Got to be careful that you don't select the wrong one. There is there are separate functions for proportions on this calculator. So we go stat, we go over to tests, and we have to arrow down a ways. Now we have one proportion z test there, but we want one proportion z interval right there. Option A, one proportion z interval. We select it. X is, what was it, 184 here? 187. N is 240 is the size of our sample. Our confidence level is 90%, so 0.90 is good, and we hit calculate. And there we get 0.7351 to 0.8232, which again, a little bit of round off error, but that's exactly what we got there. So again, the calculator saves us quite a bit of work there. And finally, we can still do a sample size calculation using proportions. We might find the minimum sample size required for the margin of error of a 95% interval for population proportion to be within 0.03. So in other words, a 3% plus or minus. So again, our margin of error formula for the population proportion is z critical times the square root of p times 1 minus p over n. If I solve this for n, we get that n equals z critical over the margin of error, that's squared, times p times 1 minus p. So for this example, 95%, we're looking at 95% inside, again, 5% outside, split half each way. So this is 2.5% or 0.025. So do an inverse normal of 0.025. Left tail is going to give us 1.960. So our z critical is 1.960. over the desired margin of error of 0.03. That's going to be squared. Times P. Now, if we don't have an estimate of P, we use P equals 0.5 because 0.5 is the worst case scenario. 0.5 is going to give us the largest required sample size. So if I put in 0.5 here times 1 minus 0.5, let's see what we get. So parentheses 1.960 divided by 0.03 squared times 0.5 times 1 minus 0.5 gives us 1067.1. Now, again, that's the minimum. So we have to round up to 1068 is the required sample size. What if we had an estimate for P? And that estimate was that P equals 0.35. Well, now this becomes N equals still 1.960 for our Z critical, still 0.03 is our desired margin of error, that's squared. But what's going to change here is this will be 0.35 times 1 minus 0.35. And this is going to be considerably smaller. So parentheses 1.960 divided by 0.03, close parentheses, squared, times 0.35 times, parentheses, 1 minus 0.35. And we get 971.07. Now, again, that's barely over 971, but it's still over 971. 971.07 is the minimum sample size. So to make it a whole number, we have to round up to 972 is that required sample size. But notice that is significantly smaller because we had an estimate of P than it would have been without that estimate of P. Okay, so that is all of the new material for this week. Does anybody have any questions? Okay, so confidence intervals are definitely a new way of thinking. I'm sure questions will come up. The nice thing is, we're at that point in the course where if you get good with the calculator does kind of take over and it can do the heavy part of the work for us. You just have to be able to look at the information given and decide, is it a Z test or a T test? Are we dealing with means or are we dealing with proportions? Those are really the only decisions you have to make. We are in week 8 here, so we're only a few weeks away from the final exam. So make sure if you don't have it yet that you start looking at signing up for ProctorU. Again, about a week before the final exam, make sure you do those diagnostic tests again on your computer. They do updates to ProctorU all the time, and I don't want someone to get caught where the update makes their computer no longer work anymore. So make sure you go through all of that. If any questions come up this week, like I said, send me a message. I'll get back to you as soon as I can. Otherwise, have a great week. I'll hang around here for a while after I shut off the recording in case anybody does want to stick around and ask questions. Otherwise, hopefully we'll see you all next Monday.
Thank
You have a good night as well.